Hello, here's the video for Chapter 5 for MAC2233, Calculus for Business and Social Sciences. We're going to be talking about finding the maxima and minima. So if we look at this graph here, notice how the graph goes up, and then the graph goes down, and then the graph goes up again. So when I talk about relative max or relative min, I'm talking about the high points would be a relative max, and the low points would be a relative min. So we have a picture where the graph goes up, down, and up again. So we can call it relative max or local max. Notice we have three relative or local max. Those would be the high points. And then a local min or a local min or a relative min would be the low points. So there'd be three of those. So if we were looking at the graph or the function, 3x raised to the 4 minus 4x raised to the third, going from -1 to infinity on the x-axis. Notice that the graph starts high, goes down, kind of plateaus, goes down a little bit more, and then goes up. We can look for relative max, relative min, or neither. So if we look at the point -1, 7, notice it's a high point, that's where the graph begins. That would be a relative max. If you look at, the definition of a max would be if you look to the left or right and it's lower, then you have a max. In this case, we don't have anything to the left, nothing exists, but to the right is lower, that would be a relative max. If we look at the point 0, 0, to the left, the graph is higher, to the right, the graph is lower, that would neither be a relative max nor a relative min. If you look at the point 1, -1, that looks like a low point, but again, we look to the left, the graph is higher. We look to the right, the graph is higher. That would be a relative min. And if you look at the point 1.5, 1.6875, it's kind of where the graph is going up. So to the left of it will be lower, to the right of it's higher. That would be neither a max nor a min in that case. We can also talk about absolute max or absolute min. Now, in order to be an absolute max, you would have to be the highest point in the entire graph. So in this graph, we have three maxes, but the last one would be the highest max. We would call that the absolute max. And as far as minimum, we have three minimums, but the lowest minimum would be the absolute min. And it is possible to have two absolute maxes or two absolute mins if they're both the highest or more than two. So when we look at that graph again of function 3x raised to the 4 minus 4x raised to the 3, the graph begins at -1, it goes down, plateaus, goes down a little bit more, and then it goes up to infinity. When I look at the point -1, 7, it is a max, as we talked about earlier, because to the right is lower. There's nothing to the left, but is it an absolute max is the question. But remember, on the end of the graph goes up forever, so this is not the highest point, so it would just be a relative max. 0, 0 was neither, so it's not a max or a min, so it can't be an absolute. 1, -1 is a minimum, and it is the lowest minimum in the entire graph. That would be an absolute minimum. And then 1.5, 1.6875 is neither max nor min, so it cannot be an absolute. So the question is, how do we find these relative max, relative min? And we call them extrema. So how do we find these extrema? Well, there's three. There's three types. They're stationary, singular, and endpoints. Stationary, singular, and endpoints. Well, first of all, what does stationary look like? Stationary are the typical high point or the low point of a graph. Stationary would be the typical high point or low point of the graph. Singular would be like a sharp corner. A sharp corner would be like a singular point. And then endpoint would be the graph begins or maybe where the graph ends. And there's three different ways of finding those. To find stationary, you take the derivative of the function, set it equal to 0, solve for x, then you can plug it back into the original to find y. So you take the derivative, set it equal to 0, solve for x, then you can plug it in to find y. A singular point, you take the derivative and find where it's not defined. An example of that would be like dividing by 0. And then endpoint, you can look at the domain to see where the graph begins or where the graph ends. So we have an example of the function 2x squared minus x to the 4 with a domain of -1 to infinity. Notice the graph starts high, goes low, goes up again, and then goes down to infinity. So, to find the stationary, we take the derivative. The derivative of 2x squared minus x to the 4 would be 4x minus 4x to the third. We set it equal to 0 and solve. Now you have to remember how to factor. So in this case, we would factor out the 4x, which leaves us with parenthesis 1 minus x squared, close parenthesis, equal to 0. We set each part equal to 0. 4x equal to 0 would be x equals 0. And we set 1 minus x squared equal to 0. And then we'd solve for x, so we'd add x squared to both sides, which would give us x squared equals to 1. Therefore, x would be positive or -1. So we have three possible, and I say possible because we have to check, three possible stationary points at 0, -1, and 1. To find the y value, we'll plug into the original. To look for stationary, we look for any, for singular, we look for any sharp corners. There are no sharp corners in the graph, but also we can do it by looking at the derivative. The derivative is 4x minus 4x to the third. There's no number I could plug in that would make it undefined. An example would be if we had x in the denominator and plugging in 0 for x would make it undefined, but there's no dividing with the x in the denominator, so there are no singular. And then endpoints come from the domain, so we have -1, which we found earlier. Endpoint would be -1. We can plug those into the original to find the choices. And if we plug into the original, so for example, if I plug 0 into the original, we get 0, 0. And if you look at 0, 0 on the graph, to the left is higher, to the right is higher, so it's a minimum, but it is not the lowest in the entire graph, so 0, 0 would be a relative min. If we look at -1, if we plug -1 into the original, -1 squared is 1, 1 times 2 is 2, -1 to the fourth is 1, 2 minus 1 is 1, so we get -1, 1. -1, 1, there's nothing to the left, but to the right is lower, so that would be a maximum. And the question is it a relative max or an absolute max? And in this case, it's an absolute max because it is the highest, and we actually have two absolute maxes. When you plug 1, you get 2 minus 1, which is 1, so 1, 1. That would also be an absolute max, because to the left is lower, to the right is lower. That would be an absolute max. So in this case, what did we find? We found two absolute maxes at -1, 1 and 1, 1. We found a relative min, because again it's not the lowest, at 0, 0. And no singular points. Okay? Again, what does a singular look like? So a singular looks like a sharp corner. So in this example, I'm just going to kind of go to, the function is x minus 1 raised to the 2/3 minus 3 parentheses x minus 1. If you look at the derivative of it, you get 2 over 3 times x minus 1 raised to the 1/3 minus 3. The point is, what number could I plug into the derivative that would make this undefined? Well, if I plug in 1, 1 minus 1 is 0. 0 raised to the 1/3 is 0, times 3 is 0. You get 0. So 1 would cause this to be undefined. And if I look at the graph at 1, that's where your sharp corner is. So that gives you an example of singular. It's a little zoomed in there where you can see that singular point at 1. It's that sharp corner, sharp corner. Okay, we'll do one example. So if we had the function x squared minus 2x from 0 to 4, and I wanted to find the max and the min, well, to find stationary, you take the derivative, set equal to 0. So the derivative of x squared minus 2x would be 2x minus 2. Set it equal to 0, add 2 to both sides. 2x equals 2, divide by 2, divide by 2, x equals 1. There's a possible stationary at 1. Singular, we look at the derivative, 2x minus 2. There's no number that would make that undefined, so there are no singular. Again, looking for something divided by x, maybe. And then endpoints would come in the domain. 0 and 4, that's where the graph starts and begins. So we know we're going to look at 1, 0, and 4. So when I go to graph this, I know I need to see x1, x0, x4. But to find the y value, you plug into the original. So if I take 1, plug into the original function of x squared minus 2x, you get -1. So we're going to look at the point 1, -1. When we plug in 0 into the original, 0 squared minus 2 times 0 gives us 0. So we're going to look at the point 0, 0. And if you plug in 4, 4 squared minus 2 times 4 gives us 8. So we're going to look at 4, 8. When I go to graph, because I would like to know what the graph looks like, remember the domain is from 0 to 4. The domain is from 0 to 4, so that's how I'll graph it. And then the y value, we need to see -1 to 8. So maybe I'd go from -2 to 10. We can graph it. It starts at 0, 0, goes down, and then goes up, but it ends at 4. And when we look at 0, 0, there's nothing to the left, but to the right is lower. So that would be a relative max. It's not the highest point. When we look at 1, -1, it is a lower point, so it's a minimum because to the left and to the right are higher. But it is the lowest point, 1, -1, so that would be an absolute min. Again, it's a stationary point. And then when we look at 4, 8, that's where the graph ends. To the left is lower, therefore it's a max, and it is the highest point in the graph, so that would be an absolute max. So in review, when we look at the function x squared minus 2x from 0 to 4, 1, -1 is a stationary point, which gives us an absolute minimum. 0, 0 is an endpoint, which gives us a relative max. And 4, 8 is an endpoint, which gives us an absolute max. And we'll do some more examples in the next video.